Hi, my name is Aishi, and today we'll be talking about metabolism and the laws of thermodynamics. So, what is metabolism? Well, metabolism is the set of processes that occur within the cells of living organisms to sustain life. And it consists of catabolism and anabolism. Now, catabolism is the breaking down of molecules. So, for example, if you have a single molecule of glucose and you break it down into two molecules of pyruvate, that would be an example of a catabolic reaction. And one of the properties of catabolic reactions is that they release energy. Now, anabolism is sort of the opposite of catabolism. These processes build up molecules, and in the process, they use up energy. So, for example, if you have, going back to the glucose example, you can build up a molecule of glucose from two molecules of pyruvate, and that would be an example of anabolism. Now let's talk about the different forms of energy. Well, energy is the capacity to cause change. And there are two forms of energy. There's kinetic energy and potential energy. Now, kinetic energy is the energy that is associated with movement. Now, one specific type of kinetic energy is heat or thermal energy. And this is the kinetic energy that is associated with the random movement of atoms and molecules, if you remember the definition of heat. And as you can see here, I've drawn an example of what kinetic energy might entail, and it's just a ball traveling through space, and it has, it's moving, it has a velocity, and so that is an example of kinetic energy, the energy that is inherent in the movement of the ball. And for heat or thermal energy, if you have a like a beaker of really hot water and a beaker of very cold water, well, this beaker, the beaker with hot water, would have molecules that are moving much faster, and there's more movement in the molecules than the beaker with cold water. Now, moving on to potential energy. Potential energy is basically anything that's not kinetic energy. It has nothing to do with movement, but it has to do with either the location or the structure of some object. So here you can see a hill, and there's a ball at the very top of the hill. So because of the location of the ball, because it's at the very top of the hill, it has the ability to basically move down the hill because gravity can do the work on the ball because of its height relative to the ground state here. And so because of its position, because it's so high up in the air, this position gives it potential energy, and so that gravity can do work on it, and it has the ability to, travel at high speeds, and some of that potential energy can be converted into kinetic energy. Now, molecules can possess potential energy based on the arrangement of the electrons in the bonds between their atoms, and the energy that is able to be released in a chemical reaction is called chemical energy. Now, what are the three laws of thermodynamics? The first law says that energy can be transferred and transformed, but it cannot be created or destroyed. So you can have energy that is going from kinetic energy to potential energy. So if you had a really fast-moving ball, and that velocity of the ball made it go up the hill, it climbs up the hill, then you have that transfer of kinetic energy into potential energy. And some of that would probably go into heat energy as well. and that's a form of kinetic energy. So it can be transferred and transformed, but it cannot be created or destroyed. You won't just suddenly have more of one type of energy when you don't have less of another type of energy within the universe. Now, the second law says that every energy transfer or transformation increases the entropy of the universe. And what is entropy? Entropy is a measure of disorder. So what this is saying is that every single thing you do, there will be more disorder within the universe. Now, the third law of thermodynamics says that all molecular movement stops at 0 Kelvin, or absolute zero. And since temperature is a measure of molecular movement, there can be no temperature lower than absolute zero. Now, sometimes people will ask, what about life? What about a cell? A cell takes in these small molecules and creates order with these molecules. It'll take these tiny ones and builds very large molecules that are really sophisticated, and there's an increase in order, a decrease in disorder. So isn't that against the second law of thermodynamics? Well, the answer is no, it doesn't go against the second law of thermodynamics, because the disorder in the surroundings actually increase, as you can see here. So here we have this cell, which is a square. We'll pretend that to be a cell or an organism, and we can see these tiny little molecules, which are the starting points for some anabolic reaction or process. And we can see that there's a lot of entropy within the cell at the moment because you have all these small molecules. And there's less energy in the environment, in the surroundings. But as you take these small molecules and you make it into a larger molecule that is more ordered, you have less disorder within this organism or cell, but you have more disorder in the surroundings. So overall, the entire universe will have more disorder and increased entropy. So how does entropy increase in the surroundings? Well, organisms will often release heat as byproducts of whatever processes occur inside the organism.